Geometrical representation of quadratic polynomials. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to reflect on what we have already covered. In our previous lesson, we explored linear polynomials, and we learned that their graphs always result in a straight line. Today, we are stepping up to a more interesting level: polynomials of degree 2, which we formally call quadratic polynomials. As we move from straight lines to these higher-degree equations, you'll notice that their visual representations are much more dynamic. Instead of just a simple line, we get curves that offer us significant insight into the nature of their zeros, helping us understand exactly where and how these functions behave. Let's get started. Understanding the quadratic polynomial. Now that we've transitioned from linear polynomials to the world of degree 2, let's take a closer look at what actually defines a quadratic polynomial. Algebraically, we represent a quadratic polynomial as p of x, which equals a x squared plus bx plus c. In this expression, the letters a, b, and c represent real numbers. However, there is one very important rule you must remember. The coefficient, a, cannot be 0. This condition is absolutely critical. Think about it. If a were to become 0, the x squared term would simply disappear, leaving us with only bx plus c. If that happens, we are no longer dealing with a quadratic polynomial. We've dropped back down to a linear polynomial, like the ones we studied in our previous lesson. So, for the polynomial to maintain its quadratic nature and form that characteristic U-shaped curve we are about to discuss, must have a value. The shape of the graph, the parabola. Now that we have defined what a quadratic polynomial looks like algebraically, let's talk about what it actually looks like when we plot it on a graph. Unlike the linear polynomials we studied in the previous section, which always result in a straight line, the graph of a quadratic polynomial is much more dynamic. Instead of a straight path, it forms a smooth, U-shaped curve known as a parabola. Now, a very important thing to keep in mind is that this U shape doesn't always face the same way. The direction in which this parabola opens, whether it points up or down, depends entirely on the leading coefficient, which is the value of a. We are going to look at the two specific cases for this in the next two slides. Case I when a0, positive. Now that we understand that the shape of our graph is a parabola, let's look at our first specific case. Suppose the coefficient of x squared is positive. When this happens, the parabola opens upwards. If you look at the screen, you'll see a visual representation that looks just like a cup or even a happy smile. In this specific upward opening shape, there is one very important feature to note. The very bottom, or the lowest point of this curve, is known as the vertex. Keep this in mind, because in our next slide, we will see how the graph changes completely if that coefficient becomes negative. Case II, when a $0 negative. Now, let's look at the opposite scenario, which we call case 2. Previously, we saw what happens when the leading coefficient is positive, creating an upward curve. But what happens if the coefficient of x squared is negative? In this case, the parabola opens downwards. If you look at the shape on the screen, it visually resembles an arch or even a frown. Because the curve is heading downwards, it doesn't have a lowest point like the previous case. Instead, it reaches a peak. This specific highest point on the curve is a very important feature known as the vertex. Keep this shape in mind, as we will see how this downward orientation applies to real-world physics in just a moment. Geometrical meaning of zeros. Now that we understand how the shape of the parabola is determined by the coefficient, let's connect this visual shape back to the concept of zeros. As we established earlier in our study of polynomial graphs, the zeros of p of x are simply the x-coordinates of the points where the graph meets or intersects the x-axis. When we apply this to a quadratic polynomial, we see something very interesting. Because of that U-shape we just discussed, the parabola can interact with the x-axis in three distinct ways. It might cross through the x-axis at two different points, it might just barely touch the x-axis at a single point, or, in some cases, it might not intersect the x-axis at all. Regardless of the shape, remember this key rule. These specific intersection points are what we call the real zeros of the polynomial. This concept is crucial because, as we will see in our upcoming real-world example of projectile motion, these points tell us exactly when an object hits the ground. Real-world example, projectile motion. Now that we have understood the theoretical shapes of parabolas, both the upward opening, smile, and the downward opening, frown, let's see how this actually applies to the world around us. A classic real-world example of a quadratic graph is the path of a ball thrown into the air. Imagine you are standing on a court and you throw a basketball toward a hoop. If you were to trace the height of that ball over time, you wouldn't see a straight line. Instead, the height follows a quadratic path. Think about the physics involved here. Because gravity is constantly pulling the ball back down toward the Earth, the coefficient a in our polynomial must be negative. As we discussed in the previous slide, a negative a creates a downward opening parabola, shaped like an arch or a frown. Finally, let's connect this back to the concept of zeros. If we look at the points where the ball would theoretically hit the ground, which is where the height equals 0, those specific moments in time represent the zeros of the polynomial describing the ball's height. This brings us to our next step, where we will perform a formal, step-by-step mathematical analysis of a specific quadratic equation. Step-by-step analysis of a quadratic polynomial. Now that we have understood the theory behind how the coefficient a determines the shape of the graph, let's put this knowledge into practice with a concrete example. Let us analyze the polynomial p of x equals x squared minus 4x plus 3 geometrically. First, let's go through step 1, which is to identify the coefficients. By comparing our example to the standard form we discussed earlier, we can see that a equals 1, b equals negative 4, and c equals 3. Next, in step 2, we need to determine the orientation of our curve. We look specifically at our value for a. Since a equals 1, which is clearly greater than 0, we can conclude that the graph is a parabola that opens upwards, just like the upward-facing smile we saw in the previous slides. In the next slide, we will take this a step further by calculating exactly where this parabola meets the x-axis. Step-by-step analysis of a quadratic polynomial, continued. Step 3 is where we find the algebraic zeros. Remember from our earlier discussion on the geometric meaning of zeros that these are the points where the graph meets the x-axis. To find them, we simply set our polynomial p of x equal to 0. So we start with x squared minus 4x plus 3 equals 0. To solve this, we can factor the quadratic expression. We are looking for two numbers that multiply to 3 and add up to negative 4, which gives us the factors x minus 1 and x minus 3, all set to equal 0. This leaves us with two solutions, x equals 1 and x equals 3. Finally, in step 4, we bring everything together to interpret our results geometrically. We take our algebraic findings and apply them to the shape we identified in the previous slide. We can now conclude that the graph of y equals x squared minus 4x plus 3 is an upward opening parabola that specifically intersects the x-axis at the points 1, 0, and 3, 0. Therefore, we can visually confirm that the zeros of this polynomial are indeed 1 and 3. Now that we have identified our coefficients and determined that our parabola opens upwards, let's move on to the final two steps of our analysis. Common mistakes to avoid. First, be very careful not to confuse the coefficient a with the constant term c. When you are trying to decide if your parabola should open upwards or downwards, do not look at the value of c. Instead, always look back at the coefficient of x squared, which is a. It is only the value of a that determines the orientation of the curve. Second, please do not fall into the trap of assuming that every quadratic polynomial must have two distinct zeros. While we have seen examples that cross the x-axis twice, remember that a parabola can also just touch the x-axis at a single point, or it might stay entirely above or entirely below the x-axis. In those cases, the polynomial has no real zeros. Finally, when you're sketching these graphs on paper, pay close attention to the shape. A common error is to draw the parabola as a sharp, pointed V shape, similar to an absolute value graph. However, as we discussed earlier, a parabola is a smooth, continuous, U-shaped curve. Avoid any sharp angles at the vertex. Now, before we wrap up our lesson and move to the final summary, I want to pause and address some common pitfalls. As we have seen through our various examples, there are a few specific mistakes that students frequently make when working with quadratic graphs, and I want to make sure you avoid them. Keep these points in mind as we head into our final key takeaways. Key takeaways. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways from today's session to ensure everything is clear. First, remember that when we move beyond linear equations to a quadratic polynomial, which we write as a x squared plus b x plus c, the graph is no longer a straight line. Instead, it forms that smooth, U-shaped curve we've been discussing, which is formally known as a parabola. Second, keep a close eye on that leading coefficient, As we saw in our step-by-step analysis, if a is greater than 0, the parabola opens upwards, creating a shape like a smile or a cup. Conversely, if a is less than 0, the parabola opens downwards, like an arch or a frown. Finally, don't forget the most important connection between algebra and geometry, the zeros of the polynomial. These are simply the x-coordinates of the points where our parabola meets the x-axis. Whether the curve crosses the axis at two distinct points, just touches it at one single point, or doesn't touch it at all, those intersection points are what define our real zeros. If you've kept these points in mind, you're well on your way to mastering the geometric representation of quadratics. Great job today!